being roughly 63 millimeters per second. From the chart, we can see that most of the entire information in here is the same as was seen in the previous slides. As all of these simulations, I couldn't see a difference of the different materials. For PTFE, these are the simulations I got, and for, as said before, I got 63 millimeters per second. For my velocity, my pressure was the same, velocity was the same for X, Y, and Z. I used Z to determine everything, as that was the direction as flow rate. And then after we did that, we were told that we needed to multiply our flow rate by 5 just to get a safe area where we know that if the blood vessel can handle this, it can handle anything the human body goes through. After multiplying it out, I got our new flow rate needed to be 23,670 millimeters cubed per second. After running these simulations, I initially noted a much greater velocity for each one, as seen in all three of these pictures, and then in the 100 millimeters as compared to the previous ones where it changed about 50% and then practically stopped at 75%. This one's solid throughout, and this is seen on all of them coming up. The main differences seen is our velocity seen on the right for the 1 millimeter tube. It has a velocity of 317 millimeters, whereas the velocity on the, that's the 10 millimeters to 100 millimeters is a 317. And then for the 1 millimeter, I actually got a lower velocity of 315 millimeters per second. And that was constant throughout. As these next ones will show, every single one, I got the same results. 317 on the right for the 10 to 100 millimeters, and then 314 to 315 for the 1 millimeter. So there was difference there compared to the lower velocity. However, they were all the same, and each material had the same velocity, so I couldn't distinguish a true difference in the material. PTFE, same thing. Velocity is all the same pressure for 0.101326 millipascals as compared to the slower velocity. Both of them had the same pressure, and the pressure didn't change as the pipe increased in length. After this was all said and done, using the simulations, I couldn't determine what material was best. The reason I came up with for this is because the materials are strong enough that at the rate that the human has blood flow, the materials can handle it easily enough that I'm not even seeing a change between all three of the materials. Because of this, all three of the materials would work, and according to my simulations. Therefore, the final decision will be based off of cost. For the peak material, using McMaster Car, which is an online parts, and you can get bolts, nuts, whatever you can there. I was able to get a section of peak material, and I found it online for $14.35 per foot, which is 5 cents for the 1 millimeter length, 47 cents for the 10 millimeter length, and $4.71 for the 100 millimeter length. For the nylon and PTFE or PTFE, I could find a lot of this in tons of different sizes. I was able to find this one for $2.85 per foot, which is 1 cent for the 1 millimeter, 9 cents for the 10 millimeters, or 94 cents for the 100 millimeters lengths. And I found this at a different website called Fluorostore, which just has a bunch of different of these flexible plastic hoses. For the polyethylene, I found it also on the Fluorostore. I found it for $2.68 per foot, which is 1 cent for the 1 millimeter, 9 cents for the 10 millimeter, and 88 cents for the 100 millimeters. Because of these findings and these costs, also stating that the simulations didn't help determine which material was going to be best. Simply just from cost, I can determine that polyethylene would be the best choice. PEEK is a very good material. I was able to find some tubes down to less than a millimeter. However, at the 9.8 millimeters, I was able to, or roughly 3/8 of an inch, so really easy to find tube length. Um, the PEEK material is really rigid, not like it's not brittle. However, there's not a lot of flex to it. So that's going back to previously stated about the metal. Nylon and polyethylene would be better choices simply because it is so flexible. So I chose to do polyethylene because it's the most flexible and because it is by far the cheapest compared to the PEEK. And I was also able to find a website called Eco Precision where they design biocompatible tubes of whatever size you needed. So they had a bunch of different sizes you can choose from, and essentially you just tell them whatever your initial internal diameter and then your wall thicknesses, and they'll make whatever material and whatever tube you need. This is nice simply because McMaster-Carr, Fluorostore, those are more like industrial hardware stores where it's not exactly where you're going to be wanting to find a artificial blood vessel, simply because you have to probably do a lot of work to it to get it sterilized and human body friendly. So Eco Precision designs them specifically for bioengineering and biocompatibility, where it is designed for medication. However, this process would be much, much more expensive. Um, I tried to get a quote from them, but you needed to quote it, and they never replied to me. Probably because I'm not looking to buy. I'm just looking to find a price for this presentation. So, as a conclusion, polyethylene, from my results and my research, is the best material to use compared to the nylon or PEEK, simply down to the cost of it. And these are the sources I used, and they are the same as my paper. Thank you so much.